and welcome to our lesson on precision DACs. In this video, we will define and discuss code-to-code glitch as well as the key methods of decreasing the glitch effect. Well, what is glitch? One specification you will commonly find documented within any DAC datasheet is glitch, or also known as glitch energy. Glitch is typically documented both as a graph and as an electrical characteristic in volt value per time division. While similar in concept to the settling time is dominated by the output buffer, while the glitch specification is actually dominated by the DAC itself. Further, glitch can also contribute to overall settling time. Glitch is defined as the energy associated with the overshoot or undershoot created by a code transition of a DAC, and is usually quantified as nanovolts per second. This can occur even when just transitioning one code, and so therefore it can also be referred to as code-to-code glitch. There are two types of glitch to be aware of. First, two-lobe glitch, and second, single-lobe glitch. Two-lobe glitch is usually associated with the impulse produced by a code transition for an R2R DAC, while single-lobe glitch is usually associated with string DACs. For two-lobe glitch, the negative component is subtracted from the positive component to give the total energy. For a single-lobe glitch, the energy is simply defined as the area of the glitch impulse itself. Two common DAC architectures are simply referred to as string or R2R DACs, as we learned in the last slide. Code-to-code glitch is typically much more pronounced in R2R code transitions, while being relatively minor during most code transitions in a string DAC architecture. For your information, when selecting a DAC on TI.com, it is also very easy to sort by architecture simply by selecting the particular parameter and choosing either R to R or string DAC. Let's first discuss the architecture of a string DAC, such as the DAC 43608, which in simple terms includes multiple resistor and switch pairs. Each pair represents a code, meaning that when you change any code, only one switch will close, while another one will open, which is when a glitch can occur as caused by the charge injection of any switch opening or closing. R2R DACs, however, are more prone to major carry transitions, which are code changes that cause a majority of switches to transition simultaneously and thus induce a larger glitch. In R2R DAC architectures, like the DAC 60501, such glitches are larger because each switch now represents a bit and not a simple code. This means that every time you change codes, you will have multiple bits changing, which means more switches changing and making the glitch larger. In addition, the R2R ladder commonly requires the use of larger switches which yield higher capacitance. The higher capacitance then increases the charge injection of each of the switches. As a result, you will typically see a signal response as follows. The initial setting of the DAC, at this point, the output is already settled from the prior state as we have just written the new value. The DAC then enters a major carry transition where all the switches are briefly connected to ground due to propagation delays of the MSB relative to the LSBs. This may be different from device to device, but it can be pronounced. The DAC then switches and settles out, and the new charge is injected, followed by a recovery time or small signal settling time. Next, we will discuss glitch reduction methods. Well, what can we do to address glitch? The first and most simple method is to add an RC filter after the DAC to decrease this glitch. Doing so will attenuate the amplitude of the glitch, but at the cost of increasing settling time just a bit. Choosing the appropriate RC ratio can be determined by looking at the period of the glitch and selecting a 3 decibel point a decade prior to the actual glitch frequency. When it comes to picking exact components, make sure that the resistance value R is kept fairly low, or else it will produce a voltage drop in combination with a resistive load. Here is an example of glitch reduction using an RC filter. Clearly you can see the trigger pulse, resulting DAC output glitch, and at the bottom the resulting function with an RC filter. The glitch is effectively minimized, though there is some resulting extended settling time in these particular cases. A second and slightly more complex way to help with glitch reduction is to use a sample and hold capacitor and amplifier technique. This method calls for a few more external components, a little extra board space, in addition to requiring strict timing, but it can provide a better result, especially for larger transitions. Using an external switch and amplifier, the glitch from the DAC's internal switching can be completely removed and left with a small transient from the added sample and hold switch. The way it is designed to work is the switch is left open as the DAC crosses over a major carry transition. Once the DAC transitions, the switch is closed, allowing the new output voltage to be set across the sampling capacitor. The capacitor will continue to hold the new voltage as the external switch is opened when the DAC is ready to update its output. This solution can effectively reduce or remove the glitch without the cost of increased settling time. The results of implementing a sample and hold circuit to alleviate glitch can be impressive. As you can see in this diagram, the glitch is greatly decreased with minimal impact to settling time. While there is still some nominal glitch toward the end of the plot, which is caused by the sample and hold switch closing, it is far less imposing than the original glitch, and in most design use cases would be acceptable as a compromise. In conclusion, in this lesson we defined and discussed the fundamentals associated with DAC glitch, also known as code-to-code glitch. Further, we discussed glitch in the context of two common DAC architectures, that of a string DAC or an R2R DAC. Finally, we illustrated two effective ways to reduce or eliminate glitch. First, either by adding a simple RC filter, which is simple to implement for minor code transitions while adding somewhat to the overall settling time, or second, by adding a sample and hold topology. While a little more complicated to implement, it is very effective at most totally removing glitch, especially for major transitions, while not adding to the overall settling time. Let's complete a short quiz to check on what we've learned today. Question number 1. String DACs typically experience major carry transitions that can be removed by the addition of an RC filter. The answer is false. String DACs typically produce a single lobe of glitch which is of small amplitude. Question number 2. Code-to-code glitch can mostly be removed from R2R DAC outputs by implementing a sample and hold topology. The answer is A, true. The sample and hold method can effectively eliminate glitch from R2R DACs with little to no increase in settling time. Thank you for watching this video on identifying and mitigating code-to-code glitch in precision DACs. To watch our other training DAC videos, please go to the ti.com/PDAC landing page as hyperlinked above.